Hi, good morning, and thanks everybody for coming. It's my pleasure to introduce Olga Demore, who is the CEO and co-founder of Semmle, an interesting tool that enforces code quality and via code queries via an Eclipse plugin. He's also a professor at Oxford University. So Olga, over to you. Thank you.
Thanks very much. I've changed the title of my talk. I'm going to talk about easy yet efficient queries over complex data. They're easy because they are simple to write. They're efficient, they're fast to execute, and they're over complex data. And by that I mean things like trees, hierarchies, and graphs. Now, I am actually going to talk about code quality tools because that's the main application that we've looked at so far. I don't believe in presenting just a completely generic technology. Rather, what I would like to show you is what you can do with it. And with this particular technology, building code quality tools is an obvious application. I should say that several of the creators of the technology are in the room at the very back. Mathieu Verbaar, Pavel Kustinov, and Neil Onkinko. Okay, code quality tools. The kind of thing that I'd like to do is to have a tool that helps find bugs, to compute metrics, to find code smells, and also just for general navigation to give different views of the code, for example, of dependencies. So what we want to do is some form of source code analysis. And typically, when you talk about source code analysis tools, people mean stuff that processes Java or C or C++, normal programming languages. But is that really right? On this slide, I've depicted the different file types that you can find in Alfresco. Alfresco is an open source content management system. And for each file type, I've plotted the number of files of that type that you find in the Alfresco source. So this is what you need in order to build Alfresco. There's an awful lot of different kinds of artifacts there. At the low end, there's some open office documents, presumably for documentation. There's some database stuff, there's some C#, there's some C header files, some DLL, some SQL, some XML, and of course, the very highest bar on this chart is Java. However, in all those 8,000 files, and over half of those are not Java. So actually, if you want to do proper source code analysis, if you want to understand what's going on in this system, it's not enough to just analyze Java source files. You also have to look at other things. And this is particularly true of an application like Alfresco. It's built on top of frameworks like Spring. And in Spring, you build components in pure Java, and then those are plugged together using configuration files in XML, which tell you how the different components wire together. And it's not possible to properly understand what the Java program does without also looking at the wiring in the XML configuration files. Another thing that is apparent from this slide is that there's an awful lot of information. It's not just the variety. There's 8,000 files, and there's over 1,000 revisions, and of course that's growing rapidly. So there's a lot of it, and it's of great variety. So this then is the vision, the task we set ourselves. And I'm not going to claim that we've actually achieved it already. This is truly what we would like to achieve in the end. This is what we're working towards. We'd want to take everything that's related to a software project. The source code, the version history, the bug reports, build scripts, databases, spreadsheets, configuration files, web pages, everything. and pass that information and store it in a central software repository. And then we want to ask questions of that repository via query engine. And of course, the kind of questions that you might want to ask depend on your role in the software project. If you're a developer, you might want to ask very detailed questions of the code, look for particular bug patterns, or you might want to look for the implications of a proposed refactoring. On the other hand, if you're a manager, you probably want to have a more high-level overview. You want to have a dashboard where you can examine the trends of how the project is progressing. Various metrics, the number of bugs, the stability of the code, and by looking at these trends, hopefully you can spot a problem early before it's become serious. And if you're a business analyst, the kind of question that you would like to ask is, if I change the business logic, what impact would that have on the code? So, if we want to make this vision come true, we'll need a software repository that can deal with all this large variety of information. And obviously, it will have to be efficient. And then also, we want to be able to query it in many different ways. So in my view, this all boils down to the following technical problem. We want to design a query engine plus a language that makes it easy to access this vast repository of different types of source artifacts. Now, it's going to be important that you can still ask your questions in the language, in the idiom of the particular problem domain that you're talking about. So it's going to be crucial that you can create libraries of queries that tailor the framework to one particular kind of artifact. So you might want to have a library for querying Java projects, or perhaps even more specifically for querying Java projects that use the Spring framework or that use Hibernate or struts. Or you might want to have a library for querying and build files, or a library for querying book databases, and so on. Now, of course, we're not the first to have this vision and the desire to solve this technical problem. Lots of people have tried before. So roughly, if you look at the literature, since 1984, there have been people trying to do precisely this, both in industry and in academia. And in industry, the main approach has been to try and store all these things in a relational database and then write SQL queries to get the information you want. And it has met with limited success. There is a little niche industry out there of so-called APM tools, application portfolio management, that does precisely that. And in academia, people have tried to apply logic programming and domain-specific query languages that are just for querying particular kinds of artifact. So there's a couple of difficulties with all these approaches. First of all, they don't scale. They just can't cope with the amount of information that we have to process. And it's important here to realize that the kind of queries that we're talking about are a lot more complex than what you would normally find in a relational database system. In particular, we will want features like recursion in order to look at paths in a call graph or look at paths in an inheritance hierarchy. Because of that, it's also quite difficult to write these queries. You can write them probably in a language like Prolog, but it's tough. You have to be an expert. And as I've already said, these domain-specific query languages are specific to just one particular kind of artifact. So I wouldn't be standing here if I didn't think that we've actually cracked it. And it's been quite a while. We started doing this kind of thing in 1996. And then around the middle of 2005, we thought we had the beginnings of a solution. And that was when we actually started thinking about making a company. And it took about 15 main years to implement the product that I'm going to show you. I'm only going to reveal here what you can do with our technology and tell you the problems it solves. I'm afraid that I'm not going to, especially as this is going to be broadcast on YouTube, I'm not going to reveal the internals. Okay, so this is our answer. It's a Eclipse plugin called SemmleCode, and it uses a query engine and query language called .QL. You can use the Eclipse plugin directly out of the box to do common tasks like navigating code, providing new kinds of views, finding bugs, enforcing coding conventions, computing metrics, understanding dependencies. And you can do all these things without caring about the fact that you actually are using this special query engine. However, if you've got some coding conventions of your own, some in-house coding conventions, some particular bug patterns that you would like to look for, it's easy to add them, typically with a query of only 3 or 4 lines in order to implement that new check and add it to the checks that are already there. So what makes it tick? This query language called .QL is object-oriented. And as I've already said, the crucial idea is that .QL allows you to create libraries. One library for every kind of source artifact that you would like to process. So a library for Java, a library for XML files, and so on. Because we're talking about code, it's all about traversing trees and traversing graphs. And so really you need recursive queries. You might want to know whether one method via a chain of other methods calls another specific method. Or you might want to check whether type T is a supertype via a whole lot of other types of a type S. Now, I've already mentioned logic programming, and thus dragons buried there. It's very easy to write such recursive queries and get terrible efficiency or even non-termination of your queries. This is one of the places where .QL is special. You can write these recursive queries, but we restricted it just enough so that it's no longer possible, or indeed it's quite hard, to write queries that are that inefficient, whereas in logic programming it's very easy. We've designed it to be very similar to Java and SQL, and indeed, in our experience, most people who start using .QL just look at a couple of examples and then start typing. It's not necessary to read a big book before getting on with it. It all runs on top of any traditional relational database. So if you've already got SQL Server, or you've already got Postgres, or DB2, Oracle, it just works on top of that, and you get all the goodies that you would expect of a industrial implementation of a programming language. We do very good error checking. I'm very proud of that because I implemented some of it myself. For example, we will warn you if a query is guaranteed to return an empty result, and in fact, that's of course the most common bug that happens when you write queries. So here is a picture of how it works, of the internals of our Eclipse plugin. The happy chappy on the right-hand side is a developer. The developer writes a .QL query using one or more .QL libraries, typically depending on what kind of thing he would like to query. A library for Java, a library from XML, a library for bug databases, something like that. Then the .QL query gets translated into an intermediate representation, and I'd like you to think of this as a kind of bytecode for search. the bytecode is not actually tied to .ql. You could translate most other query languages to it as well. So here a lot of clever magical stuff happens. It optimizes the hell out of the query, and once it's done, it actually produces procedural SQL. Now, the database vendors have made sure that all versions of procedural SQL are not quite compatible with each other. So at this point, you have to provide a template that describes the characteristics of the relational database system that you're actually using. And then that procedural SQL is actually executed on a relational database system. Yes?
I'm curious why you decided to use SQL at all rather than building on like Lucene or something like that.
So the question is whether we can, why we are building on SQL and why we're not using something like Lucene. The answer is efficiency. People have tried to use that, and for this particular application, it just turned out very difficult to achieve the performance that we're after. It probably would be easier to translate to Lucene than to SQL. Okay, back to the slides. We have so in the free Eclipse plugin, there's a number of populators that take artifacts like XML files, Java files, jar files, and store them in relational form in the database. In order to realize the vision that I started off with earlier, we would need a whole lot more of those populators. But the good news is that if you've already got such a thing, if you've already got a way of storing the data that you want to query in a relational database, then you can directly query it with .ql without doing anything special. So that database is just a normal database like any other. Okay, enough theory. Let's have a look at a demo. I'm going to explore the source of Alfresco, which is a content management system, as I've already said. It's heavily using Spring, a Java Enterprise Application Framework. Because of that, I've included the source of Spring as well. And it builds on various other libraries like Tomcat and JBoss and so on. It's a substantial project. It's not huge, but it's substantial. Over 50,000 Java methods, almost 7,000 types, and over 500 XML files. The demo is going to consist of 3 parts. I'm first going to show you this out-of-the-box functionality. So just using it to explore a code base with prepackaged queries without writing any queries. Then I'm going to show you how you can write some queries of your own. And finally, we're going to look at how you might investigate XML configuration files. Okay, what you're looking at here is Eclipse. Don't worry about the small fonts. I've made sure that the things that you really need to read will be very big indeed. So I'm going to run a package of queries, which I prepared previously. So it's already found some problems. Let me just highlight one of those. It said that there's something wrong with this compare to method. If you read the documentation of the comparable interface in the Java docs, it actually says that compare to should return 0 if and only if equals returns true. So these two things must be consistent with each other. And for example, the implementation of tree sets relies on this contract, that equality and compare to are consistent. But in this case, that's not that contract is not satisfied. Here on the first line, you can see that compare to returns 0 when one object is null and the other object is in fact not null. But the equality, the definition of equals on the same class, is just inherited from objects, so it's object equality. So in this example, the two are inconsistent. Another application of SemmleCode is that you can compute metrics. A favorite of mine when I start exploring a project is to look at the size of packages. Now, how do you measure the size of a package? One reasonable way of looking at that is to say it's the size of the API, the number of public methods that are exported from the package. And as you can see, there's one very big one of over 1,300 methods, a slightly smaller one of under 1,000. But most of the packages are between 200 and 300 public methods. Now, when you use this kind of metric, it's tempting to get all hung up about outliers, about things that are particularly bad. For example, if you have a very large method, you might say, well, that's not good at all. But it's more important to know the general trend. If there's one large method, I can probably fix it in 5 minutes by making a quick change to my code. But if the general trend is that there are many large methods in my system, I would have to do something about it. So here's an example. I've made a table of the number of lines and the percentage of methods that are actually larger than the number of lines. So there's one huge monster method of almost 1,500 lines, not good at all. But then if you go down a little bit, there's about 10% of methods that are bigger than 22, 23 lines of code. So that's, in terms of Java, for a good Java program, that's still fairly large. It's probably something that the Alfresco designers ought to watch. When you define metrics, of course, it's also often a good idea to give a particular threshold. And if the threshold is exceeded, then you want to have a look at it. And here I've done that with a metric called lack of cohesion. It tells me that this particular class, deployed file, lacks cohesion. What does that mean? Well, deployed file gives you a couple of fields. And then all that's done with that fields is to have getter methods for them. There's no method that accesses all fields simultaneously. And you could say that that's bad object-oriented design. This is just a record. It's not really properly done in an object-oriented fashion. Exploring a project often also means looking at the dependencies. And what I've done here is looking for cycles in the graph of dependencies between packages. Now, as you can see, there's some whopping big cycles there. There's a strongly connected component of size 103. And if we expand that, we can actually look at what's in there. This is not good. It's a bad piece of design in Alfresco. And it's kind of interesting that I'm not only looking at the source of Alfresco here, but also at the source of Spring. And if you know a bit about Spring, one of the big things that the designers of Spring trumpet about is that it's all about breaking dependencies. And indeed, they have been quite successful in that. If you look at these cycles in the dependence graph, they're all in Alfresco itself, but there's no such cycle in Spring. Okay, so I've already mentioned the need to look at recursive queries. And here is an example of a recursive query to compute the depth of types in the type hierarchy. As you can see, there's one outlier, one type that's much deeper than all the others. So if I click on that, I can see its password input tag. And if I double click, that actually opens the source directly. So I'd like you to notice this, that all the results of SemmleCode are very tightly integrated into Eclipse. You can have these graphs and you give these warnings, and they just a double click will send you to the relevant piece in the code. Unfortunately, in this case, it's not particularly useful. It's not particularly useful because just looking at the class itself doesn't tell us anything about how it came to be so deeply nested in the inheritance hierarchy. So here is a little graph that shows you everything above password input tag in the inheritance hierarchy. And if you follow all the arrows, it comes all the way back to object at the bottom here. And again, this is all tightly integrated in Eclipse. If I click on one of the nodes in the graph, again, it takes me to the corresponding place in the source. Okay, so let me summarize that. Using SemmleCode out of the box, there's about 115 pre-packaged queries that you can use directly to find common bug patterns. You've seen the example of compare to equals. We also have lots of queries for finding problems with cloning, with serialization, with internationalization. There's a wide suite of metrics, 42 different metrics, and for those of you who are into that kind of thing, including Robert Martin's package metrics, and there's various ways to examine dependencies. I've only shown you how to see that there are cycles, but of course the next step would be to ask, why is there a cycle? What is causing this cyclic dependency? And there's various queries that make it easy to explore that. And then there's visualization. Pie charts, bar charts, tables, graphs, warnings and errors, and easy navigation to the source. And important, if you want to show this kind of thing to a manager, you can export all the results, put them in your presentation, and show how things are going. Okay, so let's drill a little bit deeper and see how these things are written. My very first example was this inconsistency between compare to and equals. And here is the query that found that problem. So let me talk you through it. We're looking for a method m, which occurs in the source. We're not interested in matches that are somewhere in a library. Furthermore, we're looking for a method that has the name compare to. And it's not the case that if I get the declaring type and I find any method in that has the name equals. So the type that declares compare to does not declare another method named equals. And when that's the case, then we select the method m and the string missing equals. So the general form of a query in .ql is from where select. It's almost like SQL, but we flipped it around. As you shall see shortly, we flipped it around so that you can get better auto-completion. If you have declare before use of your variables, we actually know what kind of auto-completion facilities we could give you. There's another little thing to notice here. Because we have a method m and a string, when you write a query where the result is a program element and a string, you can run it as a warning and error. And when you do that, you get the squiggly in your code that gives the warning, and also in the Eclipse problems view. So let's have a look at how you actually type a thing like that. So here I'm in the .ql editor. So from method m, I typed m dot, and because we know that m is a method, we now get an option of all the different operations that you can invoke on a method. And in this case, of course, we want to have from source. Has the name compare to. Once you've written the query like that, you can run it in a variety of ways. So as I've already said, you can run it in the problem view. In this case, I'm just going to run it in the tree view. And here you've got the results. Notice that there's a little icon next to each of the results, consistent with the icons in Eclipse. So you might say, well, is this all built in? Is this all hardwired in the tool? And the answer is no. So for example, the notion of a method is just a library definition which you can look up. I've opened here I've used jump to definition, and here you've got the definition of the class method. It's a special kind of callable, a constructor or a method. There's various operations defined on it. In particular, there's the operation get icon pass. This will define what the particular icon is that's being displayed when you find one of these items in Eclipse. Of course, there's various other features in .QL that you need in order to write basic queries. So I've shown you a lot of metrics, and if you want to have metrics, then you will need to sum things, take maximums, minimums, and so on. In .QL, you might write a query for finding the total number of lines of code, for example, by selecting the sum over all compilation units. Each compilation unit CU, and provided CU is from the source, what you sum is the number of lines of code for that compilation unit. So in general, an aggregate is of the form some aggregate function, some maximum, minimum, average, number of variables, the condition that these variables have to satisfy, and then the expression, which is the thing that you're taking the sum or the maximum or the minimum of. I've also mentioned the need for recursion. If you remember, I showed you this graph of everything above a particular type. So here is an example. Here is the query that did just that. First of all, note that what we're selecting are two reference types, T and S. And T and S, so they form a binary relation, and such a binary relation can be viewed as a graph, just as I did in the demo a minute ago. So how does this query work? First, we look for the ref type it, which has the name password input tag, and then we require that it has the supertype S. It also has a supertype T, and T has supertype S. So this produces this little graph of everything above it, above password input tag in the hierarchy. There's a subtle point, however. I've used has supertype star here, and that means that we're not interested only in immediate supertypes, but possibly in a chain. So it has a supertype S0, S1, S2, all the way up to S. So this is actually a very limited form of recursion. And it turns out that in this particular application, it's often quite enough. So most recursive queries just use implicit recursion using this star operator. So let me summarize. Queries in .QL are written using from where select. You've got aggregates, which you can nest arbitrarily. There's no need for complicated things like group by, which you have in SQL. And finally, there's recursion, which is usually used implicitly with chaining, but you could also write it explicitly if that's what you want to do. Okay, I'd now like to switch gears a little bit. Go back to the demo. And what we're going to do is I'm opening a new query, excuse me, because the low resolution it has run off my screen a bit. Right. So I would now like to talk a little bit about how we can query other things than just Java code. At the very beginning, I was going on about all these XML configuration files that are also very important in a source code analysis tool. So what this query does for you, it finds class attributes in a XML file which refer to a class in your source that actually doesn't exist. So let me read through that. There's an XML attribute XA whose name is class. So it's something of the form class equals. And on the right-hand side of the equals, there is a class name. That's the value of the XML attribute XA. But the class that's being named there doesn't actually exist. There is no reference type T in our Java source, so that the qualified name of T is equal to the class name found in the XML attribute. And we're only interested in things that occur in Alfresco. So let's run that. Right, so we actually found a problem here. Let's go there. I want you to notice that I double-clicked on that and that immediately opened the relevant location in the XML file rather than just in the Java source. So here is the offending line. We've defined a class attribute that refers to a class called createTimerAction. But apparently, that thing doesn't exist. So this is actually a real bug. If you try to invoke this particular functionality in Alfresco while using JBoss, the system will crash because the relevant file is not found. So what can we do? Well, it kind of makes sense to look for another other types that have a name a little bit like createTimerAction, and then perhaps we can figure out what actually the problem was. So we're looking for some ref type T, where if you take the name of T and convert it to lowercase, then the result matches createTimerAction, possibly with some stuff before or after. And indeed, we have two results, and one of them is called createTimerAction. So let's have a look at that. Well, that's just in a class file in the JBoss library, and we're not looking for a class in a library. We were looking for a class in the Alfresco source. So let's go back. This looks a little bit more hopeful. Let's open that up. And indeed, that's just a subclass of createTimerAction, and it's in the right package, so probably this was what was intended. So let's get back to the XML file, and I'm going to fix it up. And I saved the file, and of course what's happened now is that we've withdrawn some of the old tuples from the database and put new ones back in. So at the very beginning, when you start working with the tool, you'll have to store your whole project in relational form. But then once you've done that, it's just updated incrementally. Whenever you make a change, the corresponding change is reflected in the database. Okay, so here we've got our previous query. So we're running that again. And hopefully, what we'll see is that the result is indeed. So before I had 2 results, and I've only fixed one of them. If we fix the other one in the same way, the problem is gone away. So actually, that's not how I would have written the query originally. If I'd written the query myself, I would have used the object-oriented features of .QL. In .QL, you can write new type definitions yourself. And what I've done here, I've written a type definition for a class attribute. Such a type is just a logical property. So here, a class attribute is just a special kind of XML attribute. What makes it special? Well, that's defined here in this constructor. A class attribute is a special XML attribute in the sense that its name is class. And then I've defined a number of operations on this, on class attributes, getting the class name, and getting the type. When you define an operation like that, it is just a relation between 2 special variables, this, the class attribute, and result, the thing that I want to return. And when I've done that, it's just a really short little query, which is a little bit more manageable than the one I looked at before. So let me just summarize that. In .QL, classes are just logical properties. When you write a constructor that specifies what's special about that new type you've just defined. And when you define a method, that's just a relation between this result and possibly some parameters. A slightly subtle point is that it's actually allowed to have more than one result. And finally, there's predicates, which are just logical properties like the fact that no type corresponds to a class attribute. So I'd just like to wrap up the demo with one more example. This example is taken from the Spring framework. And as I've said before, Spring is a framework for writing Java enterprise applications. And the key idea is that you define these beans that then can be wired in different ways in XML configuration files. So it's interesting to look at this wiring. And that's what this query does for me. I've defined a new class, and I'll spare you the details of that at the moment. And then the query itself just takes a bean and looks for the beans itself and any other things it refers to. So when I run that, what I will get is a graph that shows me all the beans that are defined in a particular file, plus the references that are made by that bean. And here we've got it. And it's kind of nicely symmetrical. There's 3 components here. The client ticket holder bean in the middle, then some remote services in the layer out of that, and transport at the very edge. What I'm going to do, however, is I'm going to change the example a little bit. And I'm going to display a different icon for beans. So what you see is that previously I had this picture where I used the normal icon that's common for all XML elements. And just by overriding the method getIconPath in the definition, I get a different different icon. And again, clicking on it takes me to the relevant place in the code. So let me summarize the key points of .QL. It's designed for creating libraries of queries. Classes are predicates. Inheritance is just logical implication. And you're allowed to use non-deterministic expressions. Recursive queries are possible, but they're possible with super simple semantics. It's much simpler than what you would normally find in logic programming. And finally, it's in a syntax that's familiar both to SQL and Java programmers. It's possible to write .QL classes for any database whatsoever. So just to illustrate that, I'm going to tell you how we represent methods at the very bottom level in the database itself. We've got a table called methods with various fields, the identity, ID, a name, a signature, the return type, the containing type, a compilation unit, and the location. So that's just like a normal relational schema. But what we've done here is we've actually slightly annotated it. We've introduced some extra type information. In particular, I've declared ID to be @method. And this thing we call a column type. The column type @method is just the set of elements that occurs in that column in the database. And then you can refer to that later. So for example, parent ID here is a reference to ref type. And ref type is itself defined as the union of a number of column types. So it's a little bit like what you would normally find as foreign key constraints in a database, but it's more powerful because you have things like unions of column types. Okay, once you have a column type, you can extend it by write classes of your own. So just as a mock example, here is how you might want to introduce a new class of methods. It extends the column type @method, and then I've defined a couple of operations, getName and toString, which, as I've said before, are just relations between the special variables, this and result. We've done this for all the notions that you might want for querying Java. There's about 75 class definitions and 1,000 lines of code. That leaves me just about 10 minutes to make a few concluding remarks. I always get the same questions when a couple of recurring questions when I give this talk. So let me try to preempt them and show you some answers. The most common one is to say, why didn't you use something like LINQ? Do you really need this special new query language? There's a couple of answers to this. First of all, LINQ has a different design goal. It's about object relational mappings, and it's not about creating libraries of queries. Perhaps more importantly, LINQ doesn't provide recursion. And recursion is completely key. I mean, you cannot do this kind of source code analysis without being able to do recursive queries. And finally, you cannot do these optimizations in the LINQ environment that make it all tick for us, where we specialize the use of a particular predicate to the context where it's being used. And just don't take my word for it. Eric Meyer, the creator of LINQ at Microsoft, completely agrees with the point that LINQ doesn't provide recursion and that these optimizations are essential. You might say, that all sounds a little bit too good to be true. And you would be in good company. Jeff Ullman at Stanford in 1991, when he was the leading database researcher in the world, stated quite categorically, it's not possible to have a query language that's both logical and that's object-oriented. So what's going on here? I've tried to bamboozle you into believing that .QL is both a logical query language. It's got a sound logical basis, and it's object-oriented. Well, there's two reasons. First of all, in the design of .QL, we've sidestepped some of Jeff's objections. In particular, we no longer use, he insisted that an object-oriented query language must have a notion of object identity, and we've done away with that. And secondly, there's these optimizations that I mentioned before that we do on our intermediate representation. So let me wrap up. There's 3 points that I'd like you to take away from this talk. First of all, when you do source code analysis, in source code analysis, it's just not enough to only look at artifacts that are in a traditional programming language. You also must analyze XML files and all the other stuff that is part of the source. Secondly, if you want to do that, it's completely crucial that you have an environment where you can create libraries of queries, libraries that allows you to tailor your querying environment to one particular application. And finally, I've shown you .QL, which is a solution to this problem, an object-oriented query language that makes it easy to write fast queries over trees and graphs. Thanks.